Hello guys, welcome back to my channel, Boy. It's another Simulkuy episode. Today I would like to start the simulation utility series with one of the most used utility for process engineering studies, which is the envelope utility. Envelope utility enables the user to see or observe the selected parameters for any two-phase or three-phase streams. So if you would like to know further on how to use two-phase envelope utility and three-phase envelope utility, you need to watch this video up to the end. Okay, so let's go. Okay, so I will use UniSim design to demonstrate the envelope utilities. First of all, the component list that I will use in this video is contain methane to butane plus H2O. Okay, then the fluid package I will provide Robinson and also create another one SRK. Okay, nice. So the next step, we will go to the simulation environment. I will add a material stream with the name envelope test. Okay. So to do an envelope test, we don't really need to specify the temperature, pressure, and also the flow. So the envelope will only see the fluid package that we use and also the composition of the fluid. So that's why I want to just specify the composition and also the fluid package. I will assume that they have like quite similar composition. Okay, then normalize. Okay, so that's it. We don't need to specify the temperature and the pressure or the flow. This is enough to generate the envelope. Okay, so for the utilities, we can use the shortcut control U. Okay, then we can add the envelope utility, double click or click add utility. Yep. Sorry. So the next step, we will select the stream, which is envelope test. And you could see at the top side that we use the UniSim design two-phase. So that means that we calculate the two-phase envelope. So since this is a two-phase envelope, it will be solved on a dry basis. Yeah, this is a warning because our stream has water. But if we want to calculate in two-phase, so it will be calculated in dry basis. All right. So for the first page here, the connection, we could see several parameters such as the two-phase critical temperature and pressure, and also the Craig-Condon term and Craig-Condon bar. In case you don't understand what is Craig-Condon term and Craig-Condon bar, it is the maximum temperature and also the pressure which is in the envelope region. Next, we could see the graph here. So the red line is the bubble point, the blue line is the dew point, and the yellow line is the critical point. So we can create a horizontal or vertical line as a guide for us to know the exact value by right click and then select whether you want horizontal or vertical crosshair. If horizontal, so we could see here during the x is the temperature is minus 74.38. The pressure inside the envelope is around 1160 kPa. So it will help us to know the exact value of this. If we choose the vertical, it will be like this. Yeah. Another thing is we can modify this graph in terms of the background color, also the line color. It is all able to be modified. And also you could copy to clipboard paste in PowerPoint or in your report, anywhere you want to have this information. So the envelope type itself is not only the pressure temperature envelope, but you could see there are TV, TH, PV, TH, PH, TS, and also PS. Okay, and for this PT graph, we could also check the hydrate line, yeah, by checking this hydrate. The next thing is if you want to export this data to an Excel, you could export this data by using this table. Okay, so just copy this table, you select the bubble point, the dew point, then you paste in Excel and you can create your own graph in Excel. So that's all for the two-phase envelope. Now we are moving to the three-phase envelope. We just need to select this UniSim thermal three-phase, select yes or okay. Now you could see at the performance tab that it is already generated the PT three-phase envelope. In this condition, we could also compare the envelope of different fluid package. So the current envelope is generated by PR data or PR fluid package. Now I would like to change to SRK, and you could see that it will generate a bit different value. In this position, since this is already a three-phase envelope, you could not check the hydrate, yeah, because the water is already part of this graph. Okay, so I will discuss in detail about three-phase pressure and temperature envelope because there are several scenarios that possibly happen when we try to plot a three-phase envelope for PT. Okay, so the first one is instability on the two-phase bubble line. So as you can see here, the two-phase dew line, which is shown in the blue line, is intersect with the bubble line, and this is the critical. And at the left side of the bubble, there are like three branches. The first one is the three-phase bubble, which is shown as the green line. At this point, the vapor is incipient. The three-phase incipient liquid line, which is this blue, light blue, where the liquid phase is incipient. And the third one is two-phase liquid liquid line, which is shown by this white line. And this scenario is common when the liquid forming component such as water is present, along with some heavy hydrocarbons, which is like a C7+. The next one is instability on the two-phase dew line. So if the previous one is bubble and now is the dew, so you could see that the branches is located not at the bubble side, but in the dew side. And the branch is quite the same with the previous one. There are three branches, and the three-phase bubble line that intersects one of the incipient liquid are in the three-phase critical point, yeah, which is shown in this white point. Another special thing for this scenario is the three-phase bubble line, which is shown in this green line, is intersect with one of the incipient liquid lines. Yeah, so this is the critical three-phase point. The next one is instability on both the dew and also the bubble lines. So you could see here there are two-phase dew. Yeah, the first one is the blue line and the second one is the black line, and it will intersect with the bubble line, and this intersection is the critical point. The next one is about the three-phase point, where in this case there are 2 points. The first one is in the dew point line, and the second one is at the bubble line. So that's why it's called instability on both of the dew and also the bubble. And this critical point will emerge 3 branches as you saw. And this scenario is commonly happen when the second liquid, such as water, is relatively small compared to the hydrocarbons. So the next scenario is non-instability on the two-phase dew or the two-phase bubble lines. And for this, there are 4 sub-branches of scenario. The first one is no three-phase region, where actually this is a two-phase envelope. Yeah, so it's an ordinary one. The next one is three-phase region present along with the three-phase critical point, but no two-phase critical point. So you could say at the right side is the do point, but there is no critical point here. And on the left side, there is a three-phase region and also the three-phase critical point. So that's what it means by this scenario. The next one is three-phase region present along with the two-phase critical point and a three-phase critical point. So you could see that the two-phase region is on the right side of the envelope. So we have the bubble for two-phase and also the do for two-phase, where it will meet at the critical point. And on the left side, there is a three-phase region, which also have the critical point for the three-phase. The last one is three-phase region present with two-phase critical point or three-phase critical point not present. So you could see at the right side is the do line without any bubble line. And on the left side with the green and the light blue color is the three-phase bubble line and also the three-phase incipient liquid line. And the two three-phase line is not intersect at the critical point. Okay, so that's it for this video. I hope you get more understanding in simulation utilities, especially for envelope utility, and I hope to see you in the next Simulkuy episode. Bye-bye.